Now, you may recall from earlier lecture that the diode is the key component to create rectification. Diode as a semiconductor allows current to flow in one direction but not the other direction. All these components here are rectifiers. Our power supply, we're creating full wave rectification using 2 diodes. You could also do it with 4 to create a bridge rectifier, and these are bridge rectifiers here. So when we look at our circuit, we have our center tap transformer. The center tap transformer is a split transformer, so our red wires we're not going to be studying today. The red wires are just our split, gives us an 8-volt AC output. We're not using that in our study here. I do have them tied in, so they're doing some work. They're just powering a light over here. We're going to principally focus on the blue and yellow wires here. Where the blue wire is our center tap or our ground common. Everything is going to be relative to the blue wire, so that's connected here to the negative bus rail on this side. That's going to be viewed as the common in our circuit. And then we're looking at the 2 splits, yellow to blue on the left side and yellow to blue on the right side, and they are tied into either bus rail over here on this side. So our 2 diodes creating rectification come off of each of those transformer splits. You may recall from our earlier discussion that the rectifier creates a full wave rectification that is 180 degrees out of phase when we look at our 2 diodes. So up here on our oscilloscope here, you see this is the first alteration. Ordinarily that would be then flat, but when we add that second diode in there, we see the 180 degrees second phase right here and its positive alteration. So the first diode would be positive and then off. The second diode would be off, then positive, and then it continues in its cycle. We have currently our oscilloscope settings at 2 milliseconds per division, which means that on this oscilloscope right here, 10 squares running across here, 10 times 2, we are looking at 20 milliseconds. We are essentially looking at one alteration, a little more than one alteration of our 60 hertz waveform. Counting across here, 2 humps here is one alteration. 1, 2, 3, 4, 5, 6, 7, 8, plus a couple little hashes there. 8 times our 2 milliseconds, that's 16 milliseconds, and our few hashes, that gives us our 16.7 milliseconds that we've calculated the period of this waveform to be. So we're looking at one cycle of our 60 hertz waveform, and it has currently been converted or rectified into this pulsating signal here. Now, looking at that, we want to smooth that out. So for our lab today, we're going to compare a 22 microfarad capacitor across parallel to our load. Then we'll look at a 100 microfarad capacitor parallel load, and then we'll look at a 1,000 microfarad capacitor parallel to load. We're going to see what it does to our signal. We're going to break this diode and go back to half wave rectification. So here's the oscilloscope at half wave rectification. Let's clean this up a little bit there with my trigger level. So there we are, I've got half wave rectification. Let's compare what we got by placing a single capacitor in here. So my 22 microfarad is going to go into the positive rail here, my negative rail there, and let's look up here. Look what we have going on. So we'll adjust our levels. So we lock that there. So there we are. You see the this is just a single peak. This is a charge. You come to the top of the charge, then you see the discharge. Top of the charge, and then you see the discharge. So to really make sense of this, let's put a couple more alterations up there. Again, you see charge and discharge. So you got a little noise here on my my probe. We're going to take this to, we're currently looking at it on a DC sense. Let's examine this signal on an AC sense. So there's my baseline, and on my AC sense, we can really zoom in, figure out what's actually going on here. So looking at this signal here, we can count the number of squares. I'm on 0.5 volts to the division. So my peak-to-peak ripple, 1, 2, 3, 3 times 5 is 3 times 0.5 is 1.5. Looks like we're about 1.8 volts of ripple with our 22 microfarad capacitor. Now, what happens to this signal when I add my second diode and go to full wave rectification, here we are now. We've got an extra hump. See, we go there, comes down there. It looks like the signal gets smaller. It's actually not that. We're just looking at that alteration. We're still in the same time setting here, but my peak to peak is changed. My peak to peak appears to be exactly half of what it just was, and that does make sense when we add that second alteration in there. So our peak to peak here looks like it appears to be about a 0.9. We can dial in a little closer here. I'm on 0.2 volts to the division, 2, 4, 6, 8, and we are about 0.9, which would be exactly half of our 1.8. So when we add the second rectification in, we get a little cleaner signal, we get a little smoother, more humps that are involved there. Now we're going to alter this, and we're going to compare what we get with our 100 microfarad. So put our 100 microfarad in here. We're going to take the positive lead there, negative lead there. Okay, and let's first take this back out just for our DC sense of comparison, just to clean our signal up a little bit there. Okay, looking at our DC sense, we